Okay, so the next one I'm going to do is example 14.6. And this is for the transformer. I have 100 milliamps of AC current here. Okay. Now, the ratio so the first thing it says is, what if the ratio of this is set up so it's 1 to 10? 1 turn here, 10 turns here. Okay, that means that's going to be a step up transformer. So this means that the voltage that's coming out of here will be 10 times higher. So the voltage out is going to be 10 times the voltage in. But power out has to equal power in. You can't get more power out of the transformer than you put into the transformer. In fact, you'll get actually less because of the efficiency. But this is like the maximum possible that we can get. Power out is power in, and power is current times voltage. Current times voltage. So if I get 10 times the voltage out, then I'm going to have 1/10 of the current out. Okay? So the current out will be 1/10 of the current in, which is 1/10 of 100 milliamps, which would be, of course, 10 milliamps. Now, what then, the other thing would be that they give is, well, what if this is a 2-to-1 ratio? Which means I got 2 turns for every 1 on the 2 turns on the primary for every 1 on the secondary. That is a step down transformer. Okay, so in that case, the voltage out will equal 1/2 the voltage in. That's my ratio. Voltage out is going to be 1/2 the voltage in. Oh, I'm going to sneeze. Pause it. Jeez. Okay. Sorry. Voltage out is 1/2 the voltage in, which means that the current out, by the same logic over here, the current out has to equal 2 times the current in. So that's going to be 2 times 100 milliamps, which is then 200 milliamps. Now, and so the first one, this was a step up. This one, step down. Step up in voltage. Step up is usually with voltage. Step up in voltage, step down in voltage. That's how I read it. It says, okay, then the related problem, what is the secondary current in the figure if the turns ratio is doubled? And what is the second if the turns ratio is half? Okay, so if I doubled the turn ratio, that would make this 20. Okay, so then my voltage out would be 20 times my voltage in. My current out would be a 20th of the voltage in. So this would cut this in half to 5 milliamps. Then it said over here, what if you halved the ratio? I'm not sure what they mean by halved on that. Half the ratio? That would be a 1-to-1. I think half of 2-to-1 would be 1-to-1. So if by that they mean a 1-to-1, then of course the current out will equal the current in. If what they mean is it's 4-to-1, so that's a little unclear to me what they mean by halving. So either they mean cut the two. It's either going to be 1-to-1 or 4-to-1, depending on how they interpret the question. If I said half of it, I would say 1-to-1, because half of 2 is 1. But I have a feeling that's not what they mean, because that's too easy. So in that case, if it's 1-to-1, it's current out equals current in. If it's 4-to-1, then your voltage out is 1/4 your voltage in, and your current out is 4 times your current in, so that would be 400 milliamps. So I think I'll check in the back and see which it is they had in mind. Yeah. They meant this. It's a little vague, I think. But that's what I knew that was too easy. Right? And so they need to be a little more clear on that. Okay, let me pause this, and I got another question that people have asked. Okay. Oops, I forgot to draw the picture. I'm going to draw the picture. Okay, here we have I should have left the picture up before. I've drawn the picture back, 1:4 ratio, 100 ohm load. Now, they just want you to use the formula. As you know, I often want to go a little differently. So what I'd like to do is try to explain how this works a little bit better. Okay, so I'll get the same answer, but let's suppose, just for the sake of argument, that what this is I've got a 10 volt output here. Okay. The voltage doesn't matter. I can make this whatever I want. In fact, if it mattered, then they'd have to give us a voltage, but they don't. So it's going to work whatever I have. So this is a 10 volt out AC. This is a 1:4 step up transformer, which means that coming out of here, I've got to have 40 volts AC coming on the secondary side of the transformer. Well, if I've got 40 volts and 100 ohms, then what's the current going to be here? The current is going to be voltage divided by resistance. So I got 40 volts over 100 ohms will be 0.4 amps. But from the last problem we did, remember that here the voltage out is 4 times the voltage in. The current out has to be equal to 1/4 the current in. Okay? So if I get 0.4 amps out, then the current that must be flowing over here in this circuit, this must be 4 times that. So it must be 0.4 times 4 is 1.6 amps here. So I've got, my voltage is 10 volts. My current is 1.6 amps. I forgot to draw my Ohm's law triangle, VIR. Okay, the current is again V, oops, no, I want the resistance. The resistance is V over I. Current is V over R, that was this. R equals V over I. So I have 10 volts divided by 1.6 amps equals, go to my calculator here, 10 divided by 1.6, 6.25 ohms. So, right, 6.25 ohms is the resistance that this thing sees. Okay, this is seeing in here 6.25 ohms. Why? Because it's a 10 volt source and it's 1.6 amps of current. Okay, I get 6.25 ohms is what this is experiencing. Now it's a 100 ohm load over here that's electrically isolated from it, but through the transformer, it behaves like a 6.25 ohm load. Okay, now you can walk through the example problem and you can do the little formula, and that's fine, right? But this is the sort of the why this works. Okay, so then it says if the turns ratio is, this is a related problem, if the turns ratio is 10 and the load is 600, what is the reflective resistance? So I'm going to do it the exact same way. Okay, so now I'm going to say it's 1 to 10 step up, which means that the voltage out is 10 times the voltage in. So that's going to be 10 times 10 volts, it's 100 volts out. The current out then is 1/10 the current in. But oops, sorry, I'm getting ahead of myself. So the load is 600 ohms. So the current is the voltage divided by the load. It's 100 volts divided by 600 ohms is 1/6 of an amp. Now, the current out is 1/6 of the current in. Sorry, 1/10 of the current in. So the current in is got to be 1/60th of an amp. Okay, so that's what's over here. This must be 1/60th of an amp. So the resistance that's seen by the primary is my voltage divided by my current. Again, just following what I did over here. It would be 10 volts divided by 60. 1/60th of an amp would be, I feel like I'm doing something wrong because I'm coming about with 600 ohms and that's the same as the input answer. So I think I goofed something up here. Let's see, 110, voltage out is 10 times voltage in. Voltage in was 10 volts, 10 times 10 is 100. Load was 600 ohms. Okay, so I did the 100 volts divided by 600 ohms is 1/6 of an amp. And then the current out is 1/10 the current in. Oh, 1/10. Sorry. The current out is the out, so 60th is 10 times this. So it's 10, the current in is 10 times 1/6. It should be 10/6 of an amp. So then I have 10 volts, and let's just do that on a calculator. (10 divided by 6 is 1.66. And then I have 10 volts over here by 1.67. I'm still screwing something. I know I'm still screwing something up, I think. 10 divided by 1.67. Yeah, that's back to like 6. I gotta stop and check my math. Way to go. Last lecture that I do for you all, and what am I doing? I'm getting screwed up on my math. I got to pause it for a minute to figure out what stupid mistake am I making. Well, I don't think I am making a mistake. Now, of course, if you all were here, you could be like, no, you screwed this up or you did that. It's harder to figure out the dumb mistake when you're just by yourself. But actually, I think this, I checked the back of the book, and I can't find a mistake. And if I take 10 divided by 1.67 there, right? Let me get my calculator out again. Where are you, calculator? Right. 10 divided by 1.666666 actually comes to 6. So the load is 6 ohms reflected, which wasn't what I was expecting, actually. I wasn't expecting it to be so close. That's why I was confused. Okay. But you're squaring numbers here, so you produces a little different effect than what you might expect. So there you go. So that's example 14. Oh, I've said this is 14.6. This is example 14.7. Obviously, for my last day, I'm going on the real bang of messing stuff up. So, given that, and I think I'm coming up on the time, I think I will call it quits and leave it over to you all to do your part 2s and finish her up. Adios.